In this video, we're going to play around with some hard drives on our machines. We're going to use virtual machines for this because it's very easy to create virtual hard drives and manipulate them, and we don't have to add any hardware in order to do this. So what we're going to do here, I have a couple of virtual machines running. We're going to add some new virtual hard drives to play around with. We'll go into New and choose Hard Disk. And I'm going to make a couple of VHDX disks. So I'll say Next. I'm going to make these disks dynamically expanding. Now there's a difference here between fixed size and dynamically expanding. A dynamically expanding disk, which is the default, allows the file size to start out as only 4 megabytes, and it allows it to grow over time as it needs. The fixed size will allocate all that space right at the beginning. Now this is actually much better for performance because you'll never have to worry about that file fragmenting any further than it does on that initial creation. The only problem is you can't over provision, and by that I mean a dynamically expanding disk starting at 4 megabytes, you can create plenty of large hard drives even though you have no intention of actually using up all that space, whereas with a fixed size, you're going to take up that space from your computer immediately. We look at differencing disks in a different video. So for this disk, I'm going to make it dynamically expanding, and I'm going to call this one Disk 1. And I'm going to let it save into the default path for HyperV virtual hard disks. I'm going to use the default size, even though it seems largely excessive for this testing. And there's a summary screen, and I click Finish. I'm going to do this a few more times to make a Disk 2 and a Disk 3. This way, I have a couple of disks that I can add to my virtual machine. Now those disks get created in a folder called C Users Public Documents HyperV Virtual Hard Disks. And this is all of my virtual hard disks that I've created so far. Some of them are in use right now, and some of them aren't. But you'll notice that I have this disk, and this disk, and they're 4096 kilobytes, which is 4 megabytes. That's the size of a blank, untouched virtual hard disk. At least when we make those hard disks dynamically expanding, that's the size that they begin as. So I'm going to go to HyperV Manager, and I'm going to add those hard drives to Server 1. I'm going to go into the settings of Server 1. Make sure not to go into HyperV settings. This manages the entire HyperV service. This manages simply that virtual machine. You can also get this same menu by right-clicking on your virtual machine. So you can choose settings here as well. And since I've already created those virtual hard disks, I want to click on my SCSI controller in order to add additional hard drives to my machine. Now if I were to click here on server1.vhdx, I might actually be replacing my virtual hard drive that has my operating system. So I want to be especially careful of that. I also had already added in a second hard drive called data disk. So since I already have this hard drive slot, I know I can remove that one. And then on the SCSI controller, I can choose to add a new hard drive. This is also where you'd go to add a new DVD drive if you'd like. Now I could make a new virtual hard disk right here, but instead I'm going to browse for the one that I already have. And I'm going to choose Disk 1. I'm also going to choose to add another hard drive named Disk 2. And going back to SCSI controller, I'll add another hard drive that I've already created, Disk 3. So I removed a disk and I added in 3 other disks. I'm going to say Apply to make sure all of these changes do take effect, and you'll notice the bold blue goes away from those particular changes. And I'll say OK. You may notice I did all of this hard drive manipulation while Server 1 was running, which is fine to do. I'm going to right click on Server 1 and connect to it. And I'm already logged in on Server 1, and I'm at Server Manager. For this particular activity, I'm not going to use Server Manager, so I'm going to close it. And instead, what I'm going to do is I'm going to right-click on the Start menu, on the Start button, and I'm going to choose the Disk Management utility. This is where I'm going to be able to manipulate those virtual hard disks. Now, you can see that I have my base hard drive here, my operating system hard drive. And this one was named Server 1 back here in my settings. Oops. And I can see that here. This was the very first hard drive on my computer. I also happen to have a DVD drive, and then the 3 new hard drives I've added. These disks are right here. You'll notice they say that they're offline, as well as they are unknown. They're 127 gigs, and there's even this little red down arrow here on this disk that shows that this disk is not currently operational on my system. This is usually a good thing to do. When we add a new hard drive to Windows, we don't immediately want Windows to go in and start using it for anything. We may want that disk to be protected so that in case it had some important data, it doesn't get changed without our knowledge. So what I can do is I can right-click and turn that disk online. And now this one disk is set to not initialized, and the other 2 are still offline. I'm going to turn all 3 disks online, and that allows Windows to actually take a look and start to work with those hard drives. Even though they are online, they are still not initialized, and they are completely unallocated. None of their space is in use by any volumes on my system. So the next step is actually to initialize the disk. I can right-click on any of those 3 disks and choose Initialize Disk, and I'll get a menu that allows me to select which disks I choose to initialize. I can initialize them using the old DOS-style master boot record, or I can use the newer style GPT, the GUID partition table. Master boot record has some limitations that were set way back in the day, having to do with the amount of disk space that can exist on a physical disk, the size of partitions, the number of partitions, at least number of primary partitions, and it is a little bit more susceptible to failure because the master boot record is written in one place on the virtual hard disk rather than in the GPT where it's actually stored in a couple of locations. So in most modern operating systems you may choose to use the GUID partition table. If you're concerned about backwards compatibility, continue to use master boot record. It may take a moment to initialize these disks because what it's actually doing is it's creating a partition table on that system. Now the partition table is still largely blank, but that partition table will define where partitions begin and end. You'll notice that 127 gig is a little bit smaller now. The GUID partition table does take up a little bit more space than a master boot record. I'm going to make a couple of different volume types here to test some things out. I'm going to start with disk 1, and I'm going to right click on my free space, and I'm going to choose to create a new simple volume. A simple volume is simply a chunk of disk space on a single disk. It's the most simple type of volume that you can create, and I'm going to make mine 10 gigs. And I'm going to assign a drive letter. I'm going to assign the E drive, which is the next letter that's available. You could, of course, select any other letter that you want. You can also choose to mount this new volume in an existing empty NTFS file folder on your C drive. So if there's a particular folder that you want to be actually used by a different disk, you can do that here. Or you can just skip the assignment of a drive letter or drive path. In my case, I'm going to use the E drive. I'm also going to allow this to format this disk using NTFS and the default allocation size. I'm going to call this simple because it's a simple volume. I'm going to leave the quick format enabled, and I'm going to leave file and folder compression off for now. a summary page, and I click Finish. Since I only chose to do 10 gigabytes, you'll notice that only 10 gigabytes goes out of my unallocated space. It's a healthy primary partition. Another thing you'll notice is that the 10 gigabytes here that's represented is not proportional to the amount of space in use. 10 gigs out of this should be somewhere in this area as far as disk space, but it does this so that you can most easily see your different volumes. I've got 127 almost, 126.5 gigs here. This one's 100 megabytes, but they almost have the same amount of space taken up in the GUI. So don't use the GUI as a representation for the amount of space in that chunk. The next volume type I'm going to create is I'm going to create a spanned volume. A spanned volume is kind of like a simple volume, except it allows you to span that space across multiple disks. You can consider this like a couple of different chunks of data space on multiple disks that are all just kind of globbed together in order to create a single volume. It makes great use of your disk space, although performance and reliability are somewhat sacrificed in exchange for the efficiency of using the disk space. So I'm going to use disk 1 as part of that space, and I'm going to use disk 2 as part of that space. From disk 1, I'm going to allocate another 10 gigs. From disk 2, I'm going to allocate 20 gigs. As you can see, you can use different amounts of space from each disk in order to create your volume. If I'm using 10 gigs from disk 1 and 20 gigs from disk 2, you may come to the logical conclusion that my volume will be 30 gigs large. And you'd be right. I'm going to assign this to drive letter F. I'm going to leave most of the defaults, and I'm going to call this a spanned volume. I'm also going to quick format this one. Now the first thing we're going to notice right away when we try to make a spanned volume is that this is going to convert the basic disk to a dynamic disk. And this is okay. What this is actually saying is that in order for Windows to be able to use these two disks as one logical volume, it needs to take control of those disks, and it's going to convert them to dynamic disks. Anytime you're using spanned, striped, mirrored, or RAID 5 volume types, you will need to make those disks dynamic. The problem is, as you can see in the error message, you may not be able to install other operating systems on that volume, and you may not be able to start them, because you're basically giving Windows complete control over this disk. Just be aware of that, and as long as you're using all Windows utilities to manage and work with that disk, it'll be okay to do so. Another thing that you're going to notice is the color coding for these new volume types. The color coding is different for partitions than it is for volumes. And you'll notice this key at the bottom mentions that this disk space, the C drive, is a healthy primary partition. And this E drive, even though it used to be a simple volume and a healthy primary partition, has now been converted to simply a simple volume. It doesn't even look at this as a partition anymore because the dynamic nature of this disk has taken over the partition table entirely. So it will be color coded a little different. As for my new F drive, my spanned volume, this volume expands beyond one disk. It's actually partly on two different disks. It does take up 30 gigs of space now because I've got 10 here and 10 here. And if these disks were ever to go offline, either one of them was able to go offline, the volume will be unavailable. They cannot be separated anymore. It does hurt the reliability in that regard. If either disk fails, you lose your entire volume because the volume can't differentiate between the beginning and the end of that volume. It's all one chunk of space logically in the mind of the operating system. The next type I'm going to work with, I'll right click here on the unallocated space again, is a striped volume. A striped volume allows the data to be used on multiple disks, but instead of reading the data sequentially, I'm going to read the data in stripes. If I had to read a 5 megabyte file, it's going to read 2.5 megabytes from one disk, and it's going to read 2.5 megabytes from the other disk. With both disks working together on this particular task, things will be much faster in both reading and writing. The downside is if either disk is unavailable, the entire volume is unavailable. And another downside, which may or may not be a downside to you, is that each disk has to use the same amount of space. You can't do the imbalance of space that we did with the spanned volume. If you take 10 gigs out of disk 1, you have to take 10 gigs out of disk 2. If I wanted, I could add in disk 3 as well. I can have up to 32 disks in a striped volume. And as you might logically guess, by setting up this volume with 10 gigs out of each, I get 20 gigs of capacity. I'll assign drive letter G. I'll name it a striped volume, and I will perform a quick format. I'm not prompted to create dynamic disks this time because those disks are already set to dynamic. They'll be dynamic until I wipe out all of my volumes on those disks. Next thing I can do is create a mirrored volume. A mirrored volume is going to use at least 2 disks, and it is also going to use the same amount of space from both disks. But the difference here, as you'll notice in this screen, is the capacity of that volume will only be the same as the amount of space taken out of an individual disk. And that is because the same exact data is written to the 10 gigs here as it is to the 10 gigs here. They are mirror copies of each other. If I write 1s and 0s to disk 1, the exact same 1s and 0s will be written to disk 2. Now that's not inherently efficient as far as disk space goes, but it is awfully good if one of the disks were to fail. I'll assign the drive letter H, and I'll name this a mirrored volume, and I'll perform a quick format. And lastly, I'm going to create the last of my 5 volume types in Windows 2012 R2, and that is a RAID 5 volume. I'm going to need all 3 disks for this one. All 3 disks will be necessary because 3 disks is the minimum, and out of each disk the same amount of space will be used. So I'm going to do 10 gigs out of each disk, and interestingly, when you take 10 gigs and 10 gigs and 10 gigs, you end up with 20 gigs of capacity. And that is because the way that RAID 5 works is one of the disks of the set is going to end up losing that amount of space for parity. Now the parity is technically striped across all of the disks, but it's one disk's capacity worth that is lost to parity. But the advantage of that is that any of my disks in that set can fail, and I can still access my data, and I can still recover that additional volume. I'm going to assign the drive letter I. I'm going to name this RAID 5, which is also known as striping with parity, or striping with distributed parity to be more precise. And I'll perform a quick format. And this one will also prompt me to convert disk 3 to dynamic because I am using all 3 disks. 3 disks are the minimum. This one does take a little bit longer to create, but it'll be here momentarily. And one of the things you'll notice that it will do during this startup process is it's resyncing. It's making sure that parity is in place. When disk 1 has some data and disk 2 has some data, it uses disk 3 to perform a parity calculation to determine whether or not that parity needs to be even or odd bits within that set. And that's what actually helps us determine that we can let any one disk fail. The resyncing process may take a moment, but it's not too bad. This really will depend on your disk speed. Now I can go into the E drive and I can create a file. What I'm going to do here, just as a test, is I'm going to create a text file. And here's my text. And just for simplicity, I'm going to copy this out onto my desktop, and I'll look back at my F drive and I'll copy some data in there. I'll copy some data into my G drive and my H, and now my I drive. So they all have a little bit of data in there. The resyncing process is still continuing, and that's okay, because it's just making sure that all of my parity calculations are properly in place. Now, something interesting is when this resyncing process does complete, I will be able to take a disk offline and we will be able to see what happens to our data. Which of these volumes will remain intact and which of these volumes will be utterly destroyed by losing this particular disk. Now, one thing we can do to demonstrate how our redundancy will work with our drives is we could bring our drives offline and see what would happen to our volumes. Now, I've already tried it and I actually brought my disks back online and they're resyncing now, but we can demonstrate this again. If I right click on disk 1, knowing these are actually virtual disks, I can turn that disk offline. When that happens, disk 1, in my case, is completely unavailable. You'll see that it's offline here, and you'll see that several of these volumes have failed, and some have failed redundancy. Down here, there's this missing disk. Somewhere out there, we know that there's a disk missing for all of these volumes, which is why it's failed. So we can test this out. We can take a look at our H drive. Does our H drive still work? Yes, it does. And this happens to be our mirror. And our RAID 5 drive works as well, which happens to be our striping with distributed parity. Now, to bring this back online, we could, in a physical environment, for example, we could remove the failed disk, get another disk that is the same size, and put it back in to the system, and then bring that disk online in Windows. And once we've done so, we can actually return redundancy to these volumes. Now, the volumes that had failed, the simple, the spanned, and the striped, would still remain unavailable, and we'd have to restore from backup. What I've done is I brought the original disk back online just to demonstrate how our mirrored and our RAID 5 will return to normalcy. We can right click and say reactivate disk, and when we do this, it's saying that this disk is supposed to rejoin as if nothing ever happened. Now, the reason we have to resync the mirror and the RAID 5 volumes, and we don't have to resync the simple, spanned, and striped, is because these could not have changed while this disk was unavailable. But we could have changed the contents of our mirrored volume and our RAID 5 volume. So what this is doing is it's rebuilding our parity and it's rebuilding our mirror behind the scenes to make sure that our data is fully redundant and fully protected from another failure. If we had a failure at this moment on disk 1, everything would be okay, so to speak, because this is still the good copy, if you will, and these two contain the good copy of our data, and this is the one that's actually doing resyncing. But it is going to involve both of those disks, and they're working as hard as they can right now to take this data and make sure every bit is the same on this data drive. And these likewise are doing their parity calculations to make sure parity is placed back where it needs to go. And that is basically disk management within Windows, demonstrating the 5 different volume types, demonstrating the difference between dynamic and basic disks, demonstrating how we can add a VHD or VHDX to a virtual machine, and that's pretty much all you can do within Windows Server with software volumes. There are other capabilities with hardware-based RAID, because those RAID controllers will handle your volumes outside of Windows, so you won't even see this interface. You'll just see a volume that happens to have redundancy at the hardware level. So Windows will see that completely transparently.